Hello, everyone. Welcome to my talk. This is Jordi Sastre. I'm a PhD at EMPA, the Swiss Federal Laboratories for Material Science and Technology in Switzerland. And I want to present our work on photonic methods for rapid annealing of cathode films for thin film solid-state batteries. Please bear with me. So let me first introduce what a thin film solid-state battery is, also commonly known as microbattery. It's basically a solid-state battery consisting of thin film layers in the micrometer range stacked together and normally deposited by vacuum with vacuum processes. This technology was developed in the 90s by Oak Ridge International Labs in the US, and it has become a commercial product with a small market. The main applications are small devices, microelectronics, which require low powers. For example, wireless sensors, implantable or wearable devices, smart cards, or any type of electronic or microelectronics that requires on-chip power. One of the main challenges in this technology is the crystallization of the cathode film. In order to achieve good electrochemical performance, the cathode film needs to be crystallized at temperatures of about 700 degrees for prolonged times. However, this limits severely the choice of substrates and current collectors that can be used in these devices. Typical thin film batteries are fabricated on sapphire or silicon wafers with a platinum current collector, which of course has a big impact on the cost, on the production cost. So what we try to do in our work is investigate alternative methods for crystallization of cathode films, specifically photonic-based methods. So we compare three common techniques for crystallization: flash lamp annealing, UV excimer laser, and IR laser. So flash lamp annealing consists of a xenon lamp, which emits visible light, and it's pulsed in microsecond pulses. The visible light between 200 nanometers and 1500 nanometers gives an aerial energy of around 900 joules per square centimeter. Another technique that we investigated is UV excimer laser. This is a commonly used technique in the semiconductor industry for photolithography, for example, and it's a UV laser emitting at 250 nanometers, more or less, that is capable to deliver energy densities in the order of 300 joules per square centimeter. And lastly, we also tried to use an IR laser, which is, for example, commonly used for scribing, which has a wavelength of 1024 nanometers, but it's capable of delivering much less energy densities, only about 12 joules per square centimeter. And we tried to investigate these methods with a system consisting of a spinel lithium manganese oxide deposited by salt gel method on FTO-coated glass. Here we have a comparison of the three techniques. We assessed these techniques based on three properties of the films, of the process films: the microstructure, the crystalline phase, and the electrochemical response of the cathode. We gave a evaluation to each technique based on these properties and performance. We observed that flash lamp annealing is capable of delivering as good results as with thermal annealing, whereas IR laser only cannot crystallize properly the cathode films. UV excimer laser does produce some crystallized films, but not as good as the thermal references. For example, here we have the microstructure. We see crystalline LMO after the crystallization step, the photonic crystallization step. We also observe a perfect crystalline phase, equivalent to the thermally annealed one, and also corresponding to the reference pattern. And from the cyclovoltammetry measurement, we also observe the two lithiation steps of the spinel LMO, which is what we expect from such a cathode film. In contrarily, in the IR laser measurement annealing process, we didn't observe the crystallization that we expected, and also no electrochemical response. With the UV excimer, we observe crystalline peaks corresponding to the LMO phase, but the electrochemical response is not as good as the as the thermal reference, probably because of lack of thorough crystallization. By using the FLA process LMO, we were able to fabricate a thin film battery on a temperature sensitive substrate, FTO glass, so FTO coated glass, the LMO film, which is crystallized by FLA, and then lipon and lithium metal on top. We observe we are able to obtain almost the theoretical capacity of the cathode film. Rate performance is as expected. And we also observe a very good cycle life, so only 3% degradation after 200 cycles. So in conclusion, we observed that FLA is capable of crystallizing LMO cathode films in short times, below 6 minutes, which is much less than the 1 hour thermal process used in standard thermal annealing processes. And the performance of such LMO films is comparable or even better than the thermally annealed reference. So as I mentioned, one of the main advantages of these photonic methods is that we can crystallize cathode films on temperature-sensitive substrates. So I already said in introduction, typical thin film batteries are fabricated on rich substrates like silicon wafer or sapphire, and they employ a platinum current collector. So by using FLA, we try to demonstrate an alternative processing, basically processing a thin film battery on aluminum foil, which is a common current collector in the lithium-ion battery industry, and is cheap, it's flexible, it's lightweight, and it's convenient for an industrial process. So this is how the processing looks like. We took basically aluminum foils, coated them with amorphous lithium cobalt oxide by sputtering. So no interlayers, no barriers, no additional current collector, directly onto the aluminum foil. We then use the flash annealing process for crystallization, for crystallizing the LCO into its layered oxide layer structure. Then we coated lipon as a solid electrolyte, and we deposited lithium metal as the anode. Here's a simulation of the temperature profile that is achieved with this flash lamp annealing process. So what we observe, so here the green line shows the temperature at the surface of the LCO. The dashed line is at the interface between the LCO and the aluminum, and then the gray one it's inside the bulk of the aluminum foil. What we observe is that at the surface, the LCO gets heated up to 900 degrees, which is an ideal temperature for crystallizing this cathode material, whereas at the aluminum foil, the temperature doesn't exceed the melting point of aluminum, which is 660 degrees. And this for all the time, for all the 200 pulses that are used for crystallizing these films. Here's a picture. So as it's produced on an aluminum foil, it's a bendable device. And we see here a cross-section SCM. So this is the surface. Surface is very homogeneous. So this indicates that the flash lamp annealing can crystallize the films thoroughly without producing any inhomogeneity or crack or any defect. Here's a cross section of the thin film battery, 3.3 micrometers LCO film. We see some features of the crystallization, some grains that appear after the crystallization process, the lipon electrolyte and lithium metal, which was used as anode. Here, this is the XRD of the as prepared LCO films and the ones after crystallization with FLA. So as the sputtered films show only peaks corresponding to the substrate, to the aluminum foil, and when we apply the FLA, we observe the layered structure corresponding to typical of the LCO of the lithium cobalt oxide. In both, so we investigated 3 different thicknesses, 0.7 micrometers, 1.2, and 3.3. In all 3, we observed the peaks corresponding to the LCO phase. We also did TOF-SIMS, time of flight secondary ion mass spectroscopy, to investigate the elemental distribution at the interface between the aluminum and the LCO to see if there is cross diffusion. So one of the problems of thermal annealing is that there is a lot of interdiffusion from the aluminum foil into the LCO and cobalt and lithium towards the cathode, to the current collector. But since we are using this FLA method, the temperature at the interface remains below the melting point of aluminum, so there is low cross diffusion. So this is what we observe here. The aluminum signal decays very rapidly when entering the LCO, and same for lithium and cobalt signals. So this indicates no interdiffusion, negligible interdiffusion, basically, which is a good sign for this technique. Then we, of course, we measured we evaluated the performance. So and compared this to standard rigid substrate thin film batteries and other works fabricated, or other devices that have been reported on flexible substrate or low-cost bendable substrates. So what we observe is that with our FLA technique on aluminum foil, fabricated thin film batteries on aluminum foil, we can achieve performances almost the same as on rigid substrates, and much higher, orders of magnitude higher than what has been previously reported for flexible substrates. For example, on copper or on flexible mica with a PT current collector, or on polyimide, a polymer, etc. Only this work on mica, it's comparable, but of course mica is a ceramic, so allows high temperatures sintering, but of course it complicates a lot the processing because of this need for a very thin mica substrate. And with our devices, we are even capable of powering a LED. This is a footprint of 0.15 square centimeters, and it's able to power a small LED. And here are basically the energy densities and power densities that we are able to achieve with this processing. So rather comparable to what has been previously reported for rigid substrates. And with this, I would like to conclude my talk. We investigated photonic methods as an alternative for crystallization of cathode films in thin film solid-state batteries. We demonstrated that flash lamp annealing can produce LMO and LCO cathode films with comparable properties to the ones thermally annealed. And by using this FLA method, we can produce thin film batteries on cheap, on low-cost, flexible substrate such as aluminum foil. Here are the references if you want to learn more about our work. This paper just recently came out in the Journal of Power Sources, and we are preparing a new work on these thin film batteries on aluminum foil, so please check it out if you're interested. And with this, I would like to thank you very much for your attention, and thanks our funding. And if you have questions, you are interested to learn more, you can either contact me here in the Q&A or write me an email.